even more than usual, scary as that is. Anyway, there is our, well, that's our learning intention for today. Let me back up here. So week 23 it is, believe it or not. I don't know how we're flying right along. That was our learning intention from last week. I'm going to leave it alone. Here are the three things. This is a weird way to review how in the world do you know if an equation is linear or not linear. Hey, Dion, great to see you, man. But this is three ways to know it's not linear. And so if any of these three things is true, then we can say, oh, that's not linear.
It's a mystery to Mr. Blake.
Hey there. Otherwise, we can just say it is a linear equation. So the three things are, you see I tried to circle where they're at in each equation. If you see any exponents other than 1, and usually they don't write a 1 down, then it won't be a linear equation. If you see any variables in the denominator, it's not a linear equation. Fractions are fine, just no variables in the bottom of a fraction. And then if you see any variables being multiplied together, it's not a linear equation. So those are the three things that if you can just stuff those in your head, you have a pretty easy way to say, oh, none of these are true, so it's linear. Or, oh, this one's true, so it's not linear. Okay. Any questions there, guys?
Never.
All right, then let's keep rolling. Today's agenda is probably going to end up being more Pear Deck than anything. We'll see what kind of time we have left to work on this new Alex assignment, which is just the same stuff we were doing last week with this new stuff from today tacked onto it. Okay, so our new learning intention is being able to identify a linear function from ordered pairs. When we're given ordered pairs, can we look at those ordered pairs and determine if they would be from a linear function? So I can determine if a function has a constant rate of change when given ordered pairs. That's the number one thing we're going to learn today. How do I take a set of ordered pairs and know if the rate of change is constant? And then once we understand how to do that, we'll be able to say, I can identify a set of ordered pairs as linear or nonlinear based on that rate of change. Simply, that means that if it has a constant rate of change, it is linear. And if it doesn't, then it's not linear. I can determine if a set of ordered pairs is linear by graphing them on the coordinate plane. That's not really so much part of Alex, but it definitely is part of what I wanted to make sure you understand. So that's what our day is going to be focused on. Let me pull out of here and share this Pear Deck with you. I'll just put this link into the chat. So if you just follow that link, it would take you to this activity. Your other option is start a new tab in your Chrome browser and do joinpd.com and use this code. I say the link's easier. Looks like only one person has gotten in besides me. There's another person. Woohoo! Slow but sure, we're all joining up. So we really are going to be focused on Pear Deck in more than one way today. We're using it to try and make sure we understand how to work with this rate of change idea, but we're also trying to get ourselves more familiar with Pear Deck. And it may be that I'm asking you to kind of take notes with me, and it may be that learning to use Pear Deck and how you can show your work with Pear Deck is going to be just as much of a learning part of today as the actual learning about rate of change and ordered pairs. All right, we got 9 of us in. We got a total of 12 peoples. There's 10, so that's still 9 of us in, because one of the 10 is me. So there's 3 of us not in. I'm going to leave it up to you guys, but you don't want to miss out, because this is kind of how class seems to be rolling lately. So right now we're all going to be on the same page, but as usual, toward the end, I'll make it so you can go wherever you want to go. This would be our slide from last week, and I'm not really going to spend any time on it right now, but these would be examples of what are linear equations, since all I reviewed with you earlier was how to know it's not a linear equation. So here's the slide we just looked at. I put it in our weekly slides so you could easily get to it from there. And now my question is, what you're seeing here, I'm joining up from the student side of things because that'll be an easier way for us to work together. But is what's showing up on mine the same as what's showing up on yours? So make sure that the answer to that is yes, because if the answer to that is not yes, then we're all going to be confused together. Let me know if you're not seeing that same thing that I'm looking at. So let me do a couple of other things. Yeah. So you see that slide's pretty small. What I want to do is maximize my browser window, and not just by clicking this, that won't get it there for me. But I want to actually, I could do it through the menu, but I'm about to show you the shortcut button that you can use. So if you want to do it through the menu, it would be right here and that guy. But the shortcut button on our Chromebooks, here it comes. There's your keyboard, and check that out right there. That button right above the 5 will do the same thing as what I just did with my browser. It will make it so your menus go away and things are as big as we can make them. Darn it. Oh well. So I guess the first thing we're going to learn is how to do something. Trying to decide what I want to do. Oh well. How about if we, first of all, just to make sure everybody understands, there are 5 tools down here. You got a pencil, a highlighter, a line, a text tool, and an eraser. And so with my pencil, I can just draw anywhere I want to. You see, that's a really wide drawing, but this guy right here is the sizer for all 5 of these tools. So right above the pencil, you can change the size of any of your tools. Gee, I could have made that even bigger. Now I really got a big pencil, but I can also make it really small so I can do things more accurately. Okay. Right over here is my undo button. I can start undoing all those silly things I just did. The trash can will clear everything off of your slide so you can start from scratch if you've got too much junk all over it. I say let's take our pencil tool and turn it white, so we got all these colors, and make it pretty big, because what I would like to do is get rid of this. Whoops, now I gotta undo it. I want to get rid of this line right up here, and I want to cross out function 1. I had done that, but it takes Pear Deck quite a while to update things when I try and update them. So if we just cross them all out, that'll give us space to show our work and hopefully make the most sense out of this. The next thing I would like everybody to do with me, and please don't hesitate to unmute yourself, be like, wait, Mr. Reed, or message us, whatever. Just let me know. What's up?
I'm gonna hesitate.
Are you saying, do I need to wait for a great Malcolm?
No, I said I'm gonna hesitate on purpose.
Okay, so the next thing I want to do is switch over to the highlighter. And I say let's use blue. And I want to highlight all of the X values in this set of ordered pairs. Remember, what I'm trying to do is understand, how do I know if this ordered pair, this set of ordered pairs has a constant rate of change. So the first thing I'm going to do is make sure I know which ones are x's, and I'm going to probably make that a little bit smaller so I can do this. I'm going to try and just highlight the numbers, not the parentheses or anything. So right here is a number that is an x value. It's always the first number in your ordered pairs. So there's another x value. Here is another x value. So I'm asking you guys, highlight your x values with me. I chose blue because I'm going to use text. Well, I'm going to draw in blue and I'm going to use text in blue so that we know everything that goes with working with our x values. All we're really doing is seeing how our x values change. I'm just trying to have you with me make it really clear to yourself what the heck is going on. All right, the next thing I'm doing is going back to my pencil. I'm changing it to blue and I'm making it nice and small. And I'm just going to draw an arrow, because the next thing that I'm asking myself is what was the change when I went from this x value over here to this one? I don't want it that big. I want more space than that above it because I'm going to show my work here in a minute. So I'm going to make the size of my pencil smaller, and I'm going to try and keep it much closer to the writing. You don't necessarily have to put the arrow on there, but so then I'm going to say, well, what was the change when I went from here to here? On this particular one, that's really easy, but I just want to show, let's pretend it wasn't really easy. I want to show how in the world we're going to calculate these answers. And then I got one more change to look at. When I go from that 7 to that 8, what is the change like? Okay, so hopefully you can see my arrows are just saying, well, when I went from here to here, what happened? Whew, man, I told you Mr. Reed was going to make this really hard, and you probably didn't believe me. I'm switching over to my text tool. Dang, Mr. Reed, how many tools? I want to use every tool. This is fun, man. Okay, so now you're going to type with me, I hope. I'm just going to click up here. And what was the change when we went from 5 to 6? Can somebody tell me? Because Mr. Reed just really having trouble here.
1.
Thank you. We're going to be really specific, though, because sometimes our change will be an increase and sometimes our change will be a decrease. So I'm going to say it increased by 1. And to do that, I'll put a +1. But I want to show, if it wasn't so easy for us to just see, oh, it went up by 1, Mr. Reed, how would we have calculated it? We would have taken the number that we ended up on and subtracted the previous number. So just like this, I'm going to type in 6. I'm even going to put a space, minus, space, and then the previous number was that 5. I'm going to say space equals space. I'm just putting spaces between the numbers, minus signs, equal sign, all that good stuff. And then I'm going to show, even though we don't normally say positive, we don't normally put a plus sign, for this purpose I am, because that'll make it really clear that it increased by 1. So I've typed in 6 minus 5 equals +1. I'm going to click over here, and you notice now my text box has got these little squares on it. I'm going to make it so that ends up on 2 lines. I'm going to make the, well, I thought it was. How come it doesn't like me? There it goes. I was going to put the equal sign and the 1 on the second line and the 6 minus 5 above it. And you see, you can move this wherever you want to move it, but where I want that +1 is right above this first little curve, showing that the change when I went from 5 to 6 was simply a +1. I'm going to keep doing that. I've just got to do it 2 more times. So I'm going to click up here, put another text box in. This time I'm saying, well, when I went from 6 to 7, no, that was a +1. But let's just make sure we know how we would calculate it. 7 take away 6, the number previous to the 7, equals, yes, it's another +1. So I can click over here, grab that little square. I don't know why there it goes. Didn't know why it was trying to be difficult. So there's the second one. When I went from the 6 to the 7, it increased by 1. And I'm going to do it one more time. When I went from the 7 to the 8, yeah, it increased by 1. What if I didn't know how to calculate it? Oops. I got to start with the one I ended up on, subtract the previous one. And I'm hoping you guys understand, I'm looking for this in all your hard work as well. I don't know why this text box is being super weird, but that's all right. We'll fix it in just a second. So I just had to click out of the text box and click somewhere where there was text so I could adjust things. So if you haven't figured out, Mr. Reed's kind of picky for his own stuff. Like I want mine to look like something I can make sense of. And now I understand that for these two x values, I did 6 minus 5 and realized that I got a positive 1. For these two x values, blah, 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 blah. Guess what? I'm going to do the same thing with the y values. But I'm going to switch colors. I'm going to change to green. Here's a y value. It's a 4. This y value is a 5. That just went up by 1. And this one, yep, it just went up by 1. And this one, it went up by a lot more. Oh, I said this one went up by 1. Mr. Reed does not know how to count. 5 up to 8, Mr. Reed now thinks is increasing by 1. He doesn't know what he's talking about. I admit it. Okay, here we go. I'm going to do this as fast as I can. So that means you got to do it as fast as you can too. 5, take away 4, equals. What do you know? It's a positive 1. Yep, we're going to make this really pretty too. Come on, you can do this. So, oh, I know what Mr. Reed didn't do. He didn't draw between them. We got to do that with the green. So from 4 to 5, I'll forget my arrows this time. From 5 to 8 and from 8 to 12 is what I'm calculating. Oh my goodness. Who did this in blue? It's supposed to be in green. Oh, look at that. It just changed. Okay, we can do this. Except I got to get rid of that dot. It's going to really annoy Mr. Reed. So I've been doing stuff kind of like this most of the day. It's really easy when you've already been practicing. So I know lots of you are just getting some practice in, which is just fine. All right. So there's that one. I'm going to keep going. When I go from 5 to 8, that's an increase of 3. But gee whiz, what if I needed to calculate it? I ended on an 8. I subtract the previous number, which was a 5. And my calculator tells me that's a positive 3. So an increase of 3. Do you see why I said you may be learning about Pear Deck about as much as you're learning about the constant rate of change? Well, I'm just going to go ahead and finish this before I say more. So this last one went from an 8 to a 12. So I take that 12 and subtract the previous number 8. And voila, I have a positive 4 this time. By the way, Desmos is great for doing that subtraction. If you're not sure, so far the numbers have been pretty nice, but once we get into negative numbers, I know some people would prefer to have something helping them. Okay, so we now clearly have it shown not only what the change was, positive 1, positive 1, positive 1 for the x values, and positive 1, positive 3, positive 4 for the y values. We've shown the work on how to calculate those so that hopefully we've got something to come back and look at, like, how did we do that? Oh, yeah, that's how we did that. I'll publish this as an answer key when we're all done, when I do the Pear Deck takeaways. Does anybody have a question at the moment?
Mr. Reed, I think one of our students is saying that they need a code to get into the Pear Deck. But
Just one second. If you follow the link in the chat, you don't need that code, but there's the code. So LJH. If you went to joinpd.com, it would be LJH, Z as in zebra, KT. If I was using this view, you'd see it all the time, but since I'm trying to be a kid like you guys, because I'm still really young, for sure at heart. That's the only reason you don't see it. Anybody still need that code? I didn't try and stuff it in the chat. All right. So I haven't heard any questions out there about what we just did. It's 1:30. That means we have 15 minutes of fun remaining. I heard a little sound from Malcolm, but I don't know what was being said or not said.
We snore.
Still missing it for some reason. All right, here we go. Moving right along. Remember, I'll make it so you can get back to that if you would like. This is the same idea, but I'm definitely not going to spend nearly as much time showing my work right now because I want you guys to see the rest of what's going on. So for now, I'm just going to say, we'll do blue for X's again. And when I go from, come on, Mr. Reed. When I go from this -3 to this -1, that was an increase of 2. -1 take away -3 is what we would have done. When I go from this -1 to this +1, it was an increase of 2. When I go from this +1 to this +3, it was another increase of 2. When I start looking at these y values, I have a -3 right there. When it goes to that -7, that was an, I almost tried to claim it was an increase. -3 to -7 would be going down. That was -3 degrees outside. Then it went down to -7. So that was a decrease of 4. And then I go from this -7 to this -11. That would be a decrease of 4. What I have so far would make me say this is a linear function because all the x's changed the same way. And so far, every y has changed the same way. That would be a constant rate of change, and I would be able to call it a linear function. But when we look at this last one right here, -11 went back up to -7. This was an increase of 4 right here. Again, you could calculate each one of those on your calculator, and the first two would have told you -4, and when you did -7 take away -11, you would have gotten a +4 answer. So even though the digit is the same, this is a 4 and this is a 4, one of them's a -4 because it's decreasing, one of them's positive. That makes it so that it is not a linear function. But only that one thing. Right up until that last one we checked, it sure looked like it was going to be linear. Thanks, Mr. Blake, for putting that code in the chat. Anybody have any questions at the moment? If not, we're going to keep rolling to, it's the same idea, guys, but I like this form more. Just a reminder that what we're looking at in this table right here is really ordered pairs. They're just in table form. So if I put them way over here, that top row would have been an x value of -4 and a y value of 0. And then the next one, if I actually wrote it as an ordered pair, would look like this. And we would have -2, 0 and -1, 0. So that's what they would have looked like in ordered pair form. But we're just going to use the convenience of this table. So first x value to the next x value, that's right here in this table. And right there it is. If we wanted to write out, well, how would we calculate this? It would be the number we ended up on, take away the previous number, would tell me that just increased by 1. Okay, and the same thing here. If I did -2 take away -3, I would see that it increased by 1, and it increased by 1 when I went from -2 to -1. On these values over here, hopefully it's really obvious that none of them changed. Instead of even bothering with the curve, I'm just going to put right here at the line that's in between the two numbers, the change was none, but I can represent that with +0. And here I had no change. That would be a change of 0. And here would be a change of 0. I could have written -0. I don't know why. I very much prefer +0. Who knows? But if we now look at this, all the x values were changing consistently, increasing 1, and all the y values, they were changing consistently. It's just that their change was 0. That means I have a constant change, and I can call this a linear function. These ordered pairs do come from a linear function. All right. One more and we will be done. Same idea. No, I'm sorry. There's kind of 2 more. Here we go. So on this one, when I go from 3 to 5, that's an increase of 2. 5 to 7 is an increase of 2. Same thing. 7 take away 5 would have been +2. And 9 take away 7, that's an increase of 2. +2. Over here on the y's, -9 take away -4 is going to leave me with a -5. So that would be a decrease of 5. Feels weird, but 4 degrees outside is warmer than 9 degrees. I'm sorry, -4 degrees outside is warmer than -9 degrees outside. So that truly is a decrease. And we got another decrease of 5. -19 take away -14, still decreasing by 5. Very consistent. We now see that because all the x values had the exact same change, and then all of the y values had the same change, that's when we can say it's definitely linear. Okay. One other thing I just want to mention, but it's not something we need to really know yet. This rate of change, when we're dealing with the rate of change for ordered pairs, we normally look at how the y value is changing, and a triangle, it's the Greek symbol delta, really means change in math. It's our shorthand for change. So we look at how are the y values changing in comparison to how the x values are changing. And we just figured that out 3 times. These y values changed by -5 and these x values by -2. So the actual rate of change would be -5/2 or -5/2. It's a side note, getting us ready for where we are going, not something that you have to be able to do at the moment. Okay, so it's coincidental, ladies and gentlemen, that both our tables turned out to be linear functions, and both of our sets of ordered pairs where we didn't have them in table form turned out to be not linear. That won't always happen, so don't assume that it would. All right. This is the last thing we're going to do. We're going to graph these together. I'm just going to use my pencil. Well, we'll also use the line tool this time. But I think maybe I'll use green for this first function. So you see we are still using the same functions as what we just worked with. This is the exact same function 1 we were just talking about earlier when we were figuring out its rate of change. Just in case you didn't remember, we determined that this was not linear. And so on a graph, the way we would know it's not linear is if they don't line up in a straight line. This coordinate plane is going by 2's. Each grid line represents 2 units. So that means that every grid line is going to be even numbers here, and all the odd numbers are going to end up exactly halfway between 2 grid lines. So when I see my x value of 5, I'm going over here past the 4, but not to the 6, instead smack dab in between, and then I have to go up to 4 for my y value. So right here is where the 0.5, 4 would be. The next ordered pair is 6, 5. So I'm going over. The first number tells me where to go on my x-axis. And the second number, what I need to be even with on my y-axis. So over here is 5 on the y-axis. So there is my 0.6, 5. I'm just going to pause for 1 second here and label this just to make sure everybody remembers. That's your x-axis, and up here, this up and down axis is your y-axis, just in case anybody forgot that. Okay, so back to graphing function 1. The third ordered pair is 7, 8. So the 7 tells me where to go on my x-axis. There's 7 on the x-axis. Now I got to get even with 8 on my y-axis. There's the 8. So right here is my 7, 8. And the last one is 8, 12. Kind of doesn't fit, but 8 on the x-axis is here. 12, this was 10. So if I just go up one more grid line, which would be roughly about there, that would be where 8, 12 would have been. All right, so now the question is, are they in a straight line? And that's why I want to use my line tool. I'm going to go ahead and make my line tool green. And I'm going to make my line nice and small so it doesn't hide my dots. So now I made it as small as I can make it. And I need to start, I know that my line is going to be at an angle like this. I want to start close to my lower point is how I tend to do it. And then I just start dragging my line through those 2 dots. And you see if I keep it straight, because there's no way to not have it straight, that's what my straight line would have looked like. These 2 points are on it, but these 2 points very clearly are not. That's how I know, looking at my graph, that that was not ordered pairs from a linear function. They don't all lie in a straight line or lie on the same straight line. All right, so I'm going to do the very same thing, but I think I'll switch colors for my line and my pencil to blue. So function 3 is going to be blue. We already talked about these in ordered pair form, so I'm not going there again, but -4, 0 means on the x-axis I need to find -4, and on the y-axis I need to be even with 0, or I need to move 0 units. So I'm not going up, I'm not going down, I'm staying right there on my x-axis. The next one is -3, 0, so I'm going to be right here in the middle. Then I have -2, 0, so on the -2 grid line, and then -1, 0. And I'm sure everybody can already see all 3 of those are on the x-axis, therefore they're in a straight line. But I'm going to go ahead and make a blue straight line as best I can here to show that they are clearly all on one line. That's the reason that we can say, yes, they are from a linear function. Okay, so we've learned 2 things. Constant rate of change. We figure out how much are the x values changing each time we go to a new point, and how much are the y values changing. If all the x values have the same change, and then all the y values are changing by the same amount, you have a linear function. When we graph them, if once you've got them graphed, they are all on the same line, then you know it's a linear function. Okay. Let me make it so you can go wherever you would like right now in this Pear Deck activity. And the next